Evaluating attributes. We build an abstract syntax tree, and then we add those attributes on it. And the next thing we want to do is to evaluate the attribute. By evaluating those attributes, we may find a semantic error. And then also some syntax issue. So actually, evaluate on different attribute for synthesized attribute and the inherited attributes. So we are talking about how things can be evaluated. For the attribute grammar. And evaluating attributes, the process of evaluating attribute is called annotation or declaration. So the parse tree after the evaluation of attribute is also called as decorated abstract attribute. Decorated syntax tree. I'm sorry. Or sometimes you call attributed syntax tree. Or attribute grammar, or syntax grammar, semantic grammar. There are several names. The code fragment for the loop is called semantic function. For example, we have this. And evaluating the attributes, if we have the 1 plus 3 times 2, we have the declaration of 3 like this. And then we start to evaluate the declaration. We have this expression, and then expression, and we find out it's there's a multiplication code, and then we actually evaluate this branch. It's become a parenthesis expression type, and then we go down like this, and until we find a factor that's 1, and this one pass through to here, and then we have a 3, so we pass the data here, that's 4, and then go back time, and then this is 4 and the constant 2. The reason why this attribute evaluation like this is not really to run for a data result, but is to detect the type of the data here, if it's like integer, and then if this type is actually character, then it's wrong. You will report error. In fact, we are not trying to evaluate the data for getting the result, but we actually want to do type checking, making sure that the syntactic error or semantic error can be reported. As for the long time result, we actually need to wait for a long time for division by 0 or those different things. And also, with the decorated tree, at this stage, we should add those feature for reporting runtime error into it. Top-down CFG, content-free grammar, and the parse tree for subtraction. So here we have this constant expression tail, and this, it will be expanded like this. This is LL1 expression. If we want to create attribute grammar that accumulate the value of the overall expression into root of the tree, we have a problem because subtraction is left associated. That means what is left associated? Addition is not. So this 9 minus 4 or 3 minus 4 or 4 minus 3, which one go first will make difference. That's called left associative. So we cannot summarize that the right subtree of the root is a single numerical value. We cannot summarize that. If we want to decorate a tree button up with S attribute grammar, we must prepare to describe a arbitrary number of right operands in the attribute of the tree of the topmost expression tail node. This is indeed possible, but it defeats the purpose of formalism. It requires us to embed the entire tree to the attribute of the single node. So this is actually not worthy for doing that. So that means that we need to put the type of the whole tree in order to make sure it works. Declaration with left to right attribute. So instead of doing that, for the S attribute, we use the L attribute. So the previous one actually indicate if we want to use the S attribute, everything from bottom to top, and it's left associative, then what happens is we calculate this up to there, but you still cannot decide whether the expression tail type is matching it because this minus type is left associative. So that's the problem with S attribute. If we just use that alone. And here we use the L attribute. And with L attribute, we kind of pass the attribute from the elder sibling or the parents to a certain node. This L attribute aside drawing. And S attribute is like the sun, and this L is like this. Top-down attribute grammar for subtraction. So to effectively style declaration, we need the following attribute rule. In each of the first two productions, the first rule serves to copy the left context to a subtotal. So basically, the first one is to copy what's that from parent to it. So the first one, the first attribute not being written is more like, I'm sorry. The first one we try to accomplish is to copy from the parent to child, the L shape. So this one is a subtotal. We get it from the sum. It's like this. And the second rule copy the final value from rightmost back to the root. So it's feedback. There's an S type at the end. Top-down attribute grammar for constant expression. So we have this ET, whatever, but we divide it into two rows for TT, tail, turn tails, and same for tractor tails. We can flesh out the grammar fragment to produce more complete grammar as shown. The underlying CFG for this grammar accepts the same language as the figure 4.1, but where that one was SLR and this one is LL1, and LL1 we use the L attribute. Attribute flow past this 1 plus 3 parentheses times 2 is LL1. Grammar appear in figure 4.4. Let's go to figure 4.4. This one is the LL1 grammar declaration. And then as the grammar fragment of example 4.9, the value of the left operand of each operator is carried to TT or FT production of the first subtotal, the ST subtotal attribute. The relative complexity of this attribute flow arises from the fact that operators are left associative, but the grammar cannot be left recursive for LL grammar. The left and right operands of a given operators are thus found in separate production. Grammars to perform semantic analysis for practical languages generally require non-S-attribute flow. So this one is a actually it has the L-shaped attribute. So the L-shaped attribute is not everywhere, but it's given in here, in here, and also in here, and also in here. That's an L-shaped attribute. Other attribute may be in S-type attribute. Evaluating the attributes, this attribute grammar is a good bit messier than the first one, but it's still L attributed, which means that the attribute can be evaluated in a single left to right pass over the input. In fact, they can be evaluated during an LL pass. Its syntactic attribute of left-hand side symbol depend only on the attribute of the right-hand side symbol. That's the S type. Okay, we definitely need some L type. So evaluating attribute, each inherited attribute of the right-hand side depend only on the inherited attribute of the left-hand side symbol. Syntactic and inherited attribute of symbols to the left in the right-hand side. L attributed grammar are the most general class of attribute grammar that can be evaluated in LL parser. Evaluating attributes, they are a certain task, such as generation of code for short-circuit Boolean expression evaluation, that are easier to express with non-L attribute grammar. Short-circuit one because you evaluate some data and then you branch out. So it is more efficient depending on the parent's result. Because the potential cost of complex traversal scheme. However, more real-world compiler insist that the grammar to be L attributed. Evaluating attribute flow and syntax. Previous one we talked about what attribute can be used for LL parser, but here we are talking about the evaluating attribute in terms of the mechanism. So attribute flow, there are three major attribute things for evaluating attributes. Number one, a set of rules. Number two, the action or action routines. What we want to do, the function we need to calculate, and potential rule like CFG. And the last one is the algorithm, how we run those functions. The protection rule we already know is this rule, the green one. Then the action is actually the attributes calculation function. And the last one is how we go through the tree to evaluate data. Three in combined is the design for evaluating attributes. And eventually in this chapter, we will go through a whole fully decorated tree that will run through the evaluation flow. But at this moment, we introduce the basic evaluation of the attribute flows. Attribute flow, both context-free grammar and attribute grammar do not specify the order in which attribute rules should be invoked. Both notations are declarative. They define a set of value trees, but they don't say how to build or decorate them. The order in which attribute rules are listed for a given production is immaterial. Attribute flow may require them to execute in any order. If in Figure 4.3 we were to reverse the order in which the rules appear in production 1, 2, 3, 5, 6, and all 7, it would be a pure cosmetic change. The grammar will not be altered. So content-free grammar and the attribute grammar, they work together and do not specify how attribute rules should be run. And attribute flow actually depend on the algorithm, and the algorithm determine which rule should be evaluated first. So attribute flow is an algorithm that decorates the parse tree by invoking the rule of the attribute and then calculate the functions for action routine. So action routine actually are functions. So this is called translation scheme. The simplest translation scheme is the one that makes repeated passes over the tree, invoke any semantic function whose arguments have all been defined, and stopping when they complete a pass in which no value change. Such a scheme is said to be oblivious, in the sense that it employs no special knowledge of either the parse tree or the grammar. It will hold only if the grammar is well defined. Better performance, at least for non-circular grammar, may be achieved by a dynamic scheme that tailors the evaluation order to the structure of a given parse tree. For example, by constructing a topological sort of the attribute flow graph and then invoking rules in an order consistent with the sort. And okay. One-pass compiler, a compiler that interleaves semantic analysis and code generation with parse is said to be a one-pass compiler. It is unclear whether interleave semantic analysis with parsing makes compiler simpler or complex. So if you want to mix the semantic analysis and parsing together, you actually get a one-pass compiler. If we separate them, it's a multiple pass compiler, and we actually don't know which one is better. Moreover, it is often possible to write intermediate code to an output file on the fly, rather than accumulating it in the attribute of the roots of the parse tree. This is okay. On the other hand, semantic analysis is easier to perform during separate traversal of a syntax tree. I think this is okay. So the idea is like, I don't want to read too much through this. It makes no sense. So you just need to know there are 4 types of different compilers. One-pass compiler, the compiler combining parsing and semantic analysis. Multiple pass, you separate the compiler parsing and semantic analysis. Low and go compiler, that's actually just-in-time compilation. Optimization compiler, you will optimize a lot of things to finish that. Bottom-up and top-down attribute grammar to build a syntax tree. And if you choose not to interleave parsing and semantic analysis, we still need to add attribute rule to content-free grammar, but they serve only to create syntax tree. Figure 4.5, 4.6 contains bottom-up and top-down attribute grammar respectively to build a syntax tree for constant expression. The attribute in this grammar holds neither numerical value nor a target code fragment. Instead, they point to the node of the syntax tree. Function makeLeaf return a pointer to a newly allocated syntax tree node contain the value of a constant. Okay, let's look at the things. 4.5 bottom-up semantic. grammar, and actually it's purely S attributed. Number 6 is LL parser, that's top-down L-shaped attribute. And 7 and 6 is via a button-up parse tree for figure 4.5 S attributed. 4.8 is using L attribute. Action routine, the functions. Overview of action routine. They are automatic tools that can construct a semantic analyzer, attribute evaluator for a given attribute grammar. Applications as attribute evaluator generator have been used in syntax-based editor, incremental compilers. These are different software that can use attribute evaluation generator, so that will generate action routine. Most productive compiler, however, use ad hoc handwriting translation scheme. Action routine f of x. Action routine is actually a semantic function that it allows you to do evaluation and the programmer instructs the compiler to execute at a particular point in the parsing. Most parser generators allow the programmer to specify action routines. In the LL parser generator, an action routine can appear anywhere in right-hand side. On the right-hand side. A routine at the beginning of the right-hand side can be called as soon as the parser predicts the production. A routine embedded in the middle of right-hand side will be called as soon as it appears as a match symbol overlap. So basically you have the left-hand side, it is matched, then we go into calculation of the right-hand side to get a value, go back for S attributed. That's an action function. Action routine. The implementation mechanism is simple. When it predicts a production, the parser push all of the right-hand side onto stack, including terminal, non-terminal, and the pointer to the action routine. When it finds a pointer to the action routine at the top of the parse stack, the parser simply call it and pass the appropriate attribute as grammar, argument. Top-down action routine to build a syntax tree. To make this process more concrete, consider the LLY grammar for constant expression. So LL grammar with action routine. So each one, this actually is similar to the action routine with form, but here the only difference is we associate with the action routine with the node. And this for LL grammar. And it's the ease with which the attribute grammar can be transformed into a grammar with action routine is due to the fact that the attribute grammar is L-shifted. So as you can see, L-shifted grammar is more complete. And if it requires a more complicated flow, we would not be able to cast it in the form of action routines. Recursive descents and action routines. As in ordinary parsing, there is a strong analog between recursive descent and table-driven parsing with action routine. Figure 4.10 shows the turn-tail routine from figure 2.16, modified to do so, to do its part in constructing the syntax tree. The behavior of this routine mirrors that of production 2 to 5 in figure 4.9. The routine accepts a parameter, a pointer to the syntax tree fragment contained in the attribute grammars TT1. I think this one is not really that hard. You just think about you are calling down the tree and then call the action routine functions. Don't try to make it too complicated for yourself. So here is just the node, and then you evaluate the subnodes recursive functions. So here, not only matching the node, whether they qualify input or not, and also you return the attributes, action routine in the recursive descent algorithm. Button-up evaluation. In a LR parser generator, one cannot, in general, embed action routine at an arbitrary place in the right-hand side. Since the parser does not in general know what production it is until it has seen all or most of the yield. LR parser generator therefore permit the action routine only after a point at which the production is being parsed can be identified unambiguously. This is known as the trailing part of the right-hand side, and the ambiguity part is the left corners. Button-up evaluation. If the attribute flow of the action routine is strictly button-up, say it's a S-attributed grammar, then the execution at the end of right-hand side is that is needed. The attribute grammars of the figure 4.1, 4.5, in fact, are essentially identical to the action routine version. If the action routine are responsible for a significant part of the semantic analysis, however, then they will need contextual information in order to do their job. To obtain and use this information in an LR parse, they will need some access to the inherited attribute or to the information outside the current production. Space management for the attributes. Here talking about the memory aspect of the attributes. Any attribute evaluation requires space to hold the attribute of a grammar symbol. So it's a good idea to put at the symbol table. The details differ in the button-up and top-down process. For button-up process, the S attribute grammar, the other obvious approach is to maintain the attribute stack that directly mirror the parse stack. Next to each state number on the parse stack is the attribute record for the symbol we shifted, which we enter into the state. Entries in the attribute stack are pushed and popped automatically by the parser driver. Space management is not an issue for the writer of action routines. For top-down parser, so basically button up, you just follow the stack. An extra separate attribute stack from the parse stack. For a top-down parser with L-shaped grammar, we have two principal options. The first one is to automatic but more complex than button-up grammar. It still use attribute stack, so it's one way to use a stack, but one that does not mirror the parse stack. The second option is to have lower space overhead, save time by shortcutting copy rules, and require action routine to allocate and deallocate memory. So one is using stack, one is using dynamic memory allocation. Tree grammar and syntax tree declaration. Number one, language. Button-up CFG context for grammar. I'm sorry. Button-up content-free grammar for calculator language type. Figure 4.11 contains the button-up content-free grammar for calculator language with types and declarations. The grammar differs from that of example 2.37 in three ways. We allow declaration and to be intermixed with statements. Second, we differentiate between integers and real constants. Third, we require explicit conversion between integer and real operands. The intended semantic of our language requires every identifier to be declared before it is used, and not types not mixed in the computation. So here we have different content-free grammar for the calculator language, and we allow declaration to be intermixed with the statement, and we make difference for integer and real number. So this is a new set of content-free grammar. And then it with type and declaration. So you have this type and declaration. And with this, actually, we are able to find out the semantic result, semantic meaning for the operation faster. And we can do evaluation for time matching even faster. Syntax tree to average an integer and a real. Extrapolating from example in figure 4.5, it is easy to add semantic function or action routine to the grammar of figure 4.11 to construct a syntax tree for calculator language. The other obvious structure for such a tree would represent expressions as we did in figure 4.7 and would represent a program as a linked list of declaration and statements. A concrete example, figure 4.12, contains a syntax tree for a simple program to print average of an integer and a real. So this part actually, as you can see, is more detailed. If you don't go into the code, just reading such material, it's hard to see the difference between this grammar style and that grammar style. And actually, that's a lot of implementation detail right here. And what we can see at this moment with the reading of such article is to try to imagine how the tree can be constructed and evaluated. But the best way is just to write a program or run a program to understand it. So here is a syntax tree for the calculator with type. So we have different type and different type. And this example is used as an example to conclude our discussion in Unit 1, Foundations. And this Unit 1 basically introduced the construction of compiler front end of this calculator language project. The following lecture will have its complete declarative attribute tree design for the calculator language. So basically, in this chapter 1 to 4, we introduce the front-end compiler and use the simple calculator language project. And I'm sure that in GitHub on the internet, there are tons of similar projects can be downloaded, and you can study them as well. But here, the textbook actually make it very, very theoretical. And we try to, I personally try to introduce the concept and terminology for each term. But in terms of how this language structure can be used or be built, you do really need to study the compiler design. But that's not the purpose for this course. The purpose for this course is to provide the basic understanding of the programming language and knowing all the terminology and all the mechanism for the building of a compiler. And as for the compiler design itself, it's a separate course. But in our Unit 1, basically you need to be able to comprehend how things are done in compilers, and if there is a new language, how we can develop a new language by providing proper grammars, and then do detailed design for the language. And then maybe later you take the compiler course, is able to design a compiler or interpreter for yourself. So here is one example: tree grammar and the syntax tree declaration. Real example: the tree grammar for calculator language with type. We define the states. Mask as content-free grammar describe the possible structure of parse tree for a given programming language. We can use tree grammar. And tree grammar, how much different from content-free grammar? Actually, I personally believe it's similar and the same. So it's actually talking about abstract syntax tree grammar. So it's actually a terminology, and we know in GCC compiler they use a different set of grammar. As in content-free grammar, each production rule in tree grammar represents possible relationship between parent and its child in the tree. The parent is the symbol of the left-hand side production. Child is the left symbol on the right-hand side. The production are in figure 12, 4.12. The tree grammar for calculator language with type. The notation A, column B, on the right-hand side of a production means A is a variant of B, and may appear anywhere B is expected to be. Tree grammar and content grammar differ in important way. Content-free grammar means to generate a language composed of string and token, where each string is the yield of a parse tree. A major difference. Content-free grammar means each string is the yield of the parse tree. So we use the content-free grammar to generate strings in the tree. Parsing is the process of finding a tree that has a given yield that required for you. A tree grammar, as we use it here, it means to generate the tree itself. So content-free grammar actually try to see whether something is expected. No, you roll back. And tree grammar itself will build a tree. There's no need for notion of parsing, and we can easily expect a tree and determine whether and how it can be generated by the grammar. Tree grammar for the calculator language with types. Our purpose to introducing tree grammar is to provide a framework of declaration of syntax tree. Semantic rules attached to the production of a tree grammar can be used to define attribute of a syntax tree in exactly the same way that semantic rule attached to production of a content-free grammar as used in attribute flow of the parse tree. So previous example, we use the content-free grammar. There is a certain way of decorating the attributes, and here the tree grammar claim to use the same mechanism. We use the tree grammar in reminder of this section to perform static semantic checking. So here is the definition of the term in the figure. Each node in the tree grammar, we have a name, token name, type, token type, a simple table reference that is a reference variable or a link or a pointer. Error in, error out, errors, as error message for error propagation. These are different attributes. For error propagation is also an attribute. Name is an attribute, type is an attribute, simple table. So previously we only talk about the subtotal, the value for each node. Now we add more attribute for a node, including the name, type, simple table, link, and also in and out of the errors. Inherited means an attribute from parent node is left separate, synthesized from the lower level of the tree. Tree attribute grammar for calculator language with types. A complete tree attribute grammar for our calculator language with type can be constructed using a node class, variant, and attribute in Figure 4.13. The grammar itself appears in Figure 4.14. Once decorated, the program node at the root of the syntax tree will contain a list in a synthesized attribute of all static semantic errors in the program. Each item and expression node has an inherited attribute, a simple table, link, that contains a list with type or of all identified declared to the left in the tree. Each item node also has inherited attribute errors. In that, list all static semantic errors found to the left in the tree and the synthesized attribute error out to propagate to the final error list back to the root. Each expression node has one synthesized attribute that indicates its type, and another that contains a list of any static semantic error found inside. Tree attribute grammar for the calculator language with type. Our handling of semantic error illustrated common technique. In order to continue looking for the other errors, we must provide values of any attributes that would have been set in the absence of an error. To avoid cascading error messages, we choose value for those attributes that will pass quietly through the subsequent check. In this specific case, we employ a pseudo-type code error, which we associate with any simple table entry and expression for which we have already generated a message. Tree AG for the calculator language with type. Though it takes a bit of checking to verify the fact, our attribute grammar is non-circular and well-defined. Non-circular means there is no graph, okay? And well-defined means it covers all of the corner cases. No attribute is ever assigned a value more than once. The helper routine at the end of Figure 4.14 should be thought of as macros rather than a semantic function. For the sake of brevity, we have passed them to the entire tree node as argument. Each macro calculates the value of two different attributes. Under a strict formulation of attribute grammars, each macro would be replaced by two separate semantic functions, one per calculated attribute. And class of a node, we have different nodes. A variant are the symbols, and then inherited attribute, synthesized attribute. So this one is to show you each node and their attribute other than the arithmetic functions or action routines. Here are the tree related and error related attributes so that you can actually use that to find a simple table entry and also find the error propagation scheme. So here we write the grammar rule into this. And more and more. These are just writing the grammar. So as you can see here, the calculator language has a complete definition by the tree grammar. And we don't go into the detail for each statement because it takes too long a time. But basically, as you can see, tree grammar has more attribute compared to context-free grammar, and the syntax tree are built upon the context-free grammar. And tree syntax actually is very useful for compiler design. Decorating a tree with AG of the AG tree. We have the decorated AG in 4.15, the tree grammar in 4.14, and the syntax tree in 4.12. These three are the same one project. Simple table information flow along the chain of the items and down to the expression tree. The integer declaration and real declaration node add new information. Other nodes simply pass the table along. Decorating a tree with attribute grammar of the attribute grammar tree. In our example grammar, we accumulate error messages into a synthesized attribute of the root of the syntax tree. In an ad hoc attribute evaluator, we might print this message on the fly as the error were discovered. So basically, we try to detect the syntax error, and then we pass along the ID of the error, and then sum up to the root node, and then we can do one pass to print out every error. Or maybe along the way of evaluating, you print the result out partially. One could convert our attribute grammar into executable code using the automatic attribute evaluator generator. Alternatively, one can create an ad hoc evaluator in the form of mutually recursive subroutines. In later case, attribute flow would be explicit in the calling sequence of the routines. We could then choose if desired to keep the simple table in global variables rather than passing it from node to node through attributes. Most compilers employ ad hoc approach. Here is the result for the declaration of syntax tree for grammar 4.12 and the tree grammar 4.14. Okay, we finish Unit 1. And in Unit 1, basically, this chapter discussed the task of semantic analysis. And I know the first part we talk about GCC is more concrete, more something you really know in which step, what result we will get. The second part, when we talk about a syntax tree, semantic tree, dynamic syntax, static syntax, the topic is a little bit dry because actually it's so much grammar and so much things just texical and not really graphical to represent it. And in fact, if you don't dive into those coding, I actually don't imagine you can really grab the whole concept. So if it's possible, you try to build a parser of yourself, try to do a parser and semantic tree analysis yourself. That's the best suggestion. We also consider the role a semantic analyzer plays in a typical compiler. We noted that both the enforcement of static semantic rule and the generation of intermediate code can be cast to in terms of annotation, declaration, and the part tree or syntax tree. We then presented attribute grammar as a formal framework for this declaration process. So half of the middle end is in GCC is this attribute grammar generation over here, and we try to avoid the error and also optimize the stages, and before release the machine code. Other chapters in subsequent chapters 6 to 10, Unit 2, we will consider a wide variety of programming language constructs. Rather than present the actual attribute grammar are required to implement these constructs, we will describe their semantics informally and give example of the target code. We will return to attribute grammar in chapter 15, and when we will consider generation of intermediate code. That's a backend for compilers. Okay, thank you. Bye now.